Hello everyone. Today we're going to begin the Thermochem unit. I intend today to be a brief introduction. I'm going to try to keep this video as short as possible and just highlight the important things. Okay, you are more than welcome to look through the presentation more in depth at your will, but I'm going to try to just cover everything that I want you to understand. And Thermochem, again, focuses on the energy aspect of chemical reactions. So today I want to focus on the two options that you have. When a chemical reaction happens, it's either going to gain energy or lose energy. Those are your only two options. Okay, it's either going to gain it or lose it. So when we talk about energy, we need to understand what types of energy exist. Okay, you have gravitational energy. All of these things, okay, you may or may not have had physics yet. I know most of you are sophomores, but you're going to see all of this eventually, but you don't need to have taken physics to understand this part of things. Okay, this will make sense. So you have gravitational energy, which is essentially has to do with height. Okay, the higher something is, the more gravitational energy it has because it is further from the ground. So it has more time to fall. So that's what's referring to. You have elastic energy with springs and rubber bands. You have electrical energy, okay, things like batteries and currents. And then you have the energy of motion. The energy of motion is considered to be kinetic energy, okay? These are the different types of energy that exist. The one that we're going to be focusing on, and which actually isn't listed here, is heat, okay? When chemical reactions happen, either heat is being released or being absorbed, okay? You're either going to have a temperature increase or a temperature decrease. That's what you're going to have more often than not. Some new vocab that I need you to get down in order to make things easier to explain is the word system. You have a system and you have surroundings, okay? You have a system and you have surroundings, okay? I want to go through this first before I continue. So when they're talking about a system, they're just referring to wherever the chemical reaction is taking place, okay? So let's pretend this is our beaker and the beaker has some liquid in it and the reaction is taking place in the liquid, okay? It's happening in here. That is our system. Everything else, absolutely everything else in the world is the surroundings at that point, okay? And that includes the container. Let's say this is a glass beaker. The glass beaker is the surrounding. Anything else around it is the surrounding. If you were touching it, your hand is a part of the surroundings. The only thing that's considered the system is the liquid or wherever the chemical reaction is taking place. So that's what they mean by system and surroundings. Okay. Okay. So when a chemical reaction takes place, that is your system. And that system is either going to gain energy or it's going to lose energy. That value, it has a unit of joule, okay? Joule is what we use to label or define energy. It can be used for motion, it can be used for elastic, it's used for all type, including heat, okay? So when we're quantifying or trying to figure out how much energy is gained or lost, the unit is a joule. Okay, it's a joule. Whether you know it or not, you are already kind of familiar with the joule. If you've ever worked with anything electrical, I'm sure you guys have all heard of the term watt. Okay, a watt, a light bulbs. You may have seen them on light bulb container. Okay, watt is basic. It's a unit of power. There's power in energy. I'm not going to get into it, but just know that a watt is the same thing as a joule per second. Okay, a watt is a joule per second. So if you understand watt, you already kind of understand joule. Okay, they are synonymous. They go together. Okay, but joule is just a unit for energy. Okay. And on food, when you look at the nutrition facts on food, you see that they have it in calories. Calorie is another unit of energy, okay? And I want you to note something here. On the nutrition labels, you're going to see calories with a capital C, okay? Notice how they have here 1 calorie with a capital C is equal to 1,000 calories with a lowercase c. They are not the same thing. Technically, this is considered a kcal or a kilocal, okay? So all the labels on your food, they are technically in kcal, okay? You're more than welcome to Google that, and if you want to research that a little more, but this is just for you to be aware, okay? But joule and calories are how we measure energy, okay? Calories for food and joules for everything else, okay? Remember, I previously put A little thing about calorimetry. Okay, calorimetry is how they figure out how much energy is in your food, and what that tells you is the energy comes from the bonds. When your body processes the food and breaks it down and breaks apart all the bonds, that's how much energy it can get out of it. Okay. Now, I want to make sure that there are no misconceptions. People often mix up energy and heat. Heat is a type of energy. Okay, energy can be transformed into different things. Okay, so the heat itself is not an energy value. Like, you can't quantify that, but heat is the result of energy, if that makes sense. Okay, so let's say something is 100 degrees Celsius. Okay, boiling boiling water is really hot. That system, that boiling water, has a lot of energy, and a lot of the energy is being converted into heat. That's why it gets hot. So the heat itself is not the value that you're looking for. The heat tells you, oh, this is hot, therefore this has a lot of energy. Okay, if that makes sense. I know that sounds a little confusing, but I want to make sure that there's no misconceptions. They are not the same thing. Energy can take different forms. Okay, so let's say instead of getting hot, the water started moving. If it had the ability to move. Nope, give me one moment, please. Someone is at the door. I will be right. Okay, I am back. Pardon the interruption. My apologies. Where was I? I was explaining the difference between energy and heat, and I don't want you guys to think they're one and the same. So best example I can give you is when you rub your hands together. When you rub your hands together, you produce friction, right? And that friction makes your hands hot. But that's not the only thing that you get. Okay, when you rub your hands together, you can also hear it. You can hear the rubbing. You rub your hands together, it makes a sound. Okay, so what that means is all of the energy is not going into heat. If all of it went into heat, then there would be no sound. It would be complete silence. Okay. Whenever you hit something, whenever something bangs together, it makes a sound. Producing sound requires energy. Okay. The reason I bring that up is I want you to understand that when something is hot, it does have a lot of energy. But just because something is not hot does not mean that it does not have a lot of energy. There are different types of energy. Okay, they are not one and the same. Okay, but just don't confuse heat with energy. Don't think just because something is cold that it doesn't have a lot of energy. It depends on the context. Depends on what we're talking about. Okay, but I want you to separate them. They are not the same thing. Energy and heat do not go together. Well, they do go together in the sense that one is a form of the other, but they do not equal each other. Okay, energy does not equal heat. Okay, it's not the only thing you can get. Okay, now with that in mind, I want to start talking about energy transfer. When you put ice cubes in a drink, what happens to the temperature of the drink? It goes down. But what happens to the temperature of the ice? It goes up. Okay. When you have two things that are not the same temperature come in contact with each other, you have energy transfer. Okay. And it always goes from higher to lower. Okay. So the energy is going to go from the warmer thing to the colder thing. That's how it works. Okay. Temperature gradients. It always goes from high to low. High concentration, low concentration. Whatever gradient you're thinking of, it always goes from high to low. High pressure to low pressure. High temperature to low temperature. That's the flow. That's how it always happens. So on the left here, we have object A at 20 degrees, and on the right, we have object B at 10 degrees. They're touching, so you're going to get energy transfer from A to B. And that energy transfer is going to keep happening until they become equal, okay? So temperature B is going to go up and temperature A is going to go down. And that's going to keep happening until they're equal, okay? Now, it's not always one to one. What I mean by that is It's not going to be dead smack in the middle. It depends on the material. So this, you might be tempted to say, okay, then that means this is going to go down to 15 and this is going to go up to 15. Okay, so then this would be plus 5 and then this would be minus 5. That is not necessarily true. That's a conversation for another day, but just know that that is not necessarily true. It is not going to be an equal straight up transfer, okay? That's not how it's going to happen. So that's a conversation for another day. But just know that you have energy transfer from the high temperature thing to the low temperature thing. Okay. This is a review slide. First law of thermodynamics: energy cannot be created or destroyed. Okay, it can only be transferred. Okay, so they're just using this graph to designate systems and surroundings again. Okay, so if energy is lost to the surroundings, what that means is that the chemical reaction became warmer than the surroundings, and the only way that can happen is if it released energy. Okay, so let's say you have a liquid. The liquid is 20 degrees, and then you combine it with another liquid, and then it gets hotter. Then it goes up to 30. The only way that could happen is if a chemical reaction took place and energy was released. Okay, the energy had to be released and converted into heat. That's what made the temperature go up. Okay, so that is energy being lost to the surroundings. Again, the surroundings is anything that is not the reaction. Okay, if you put a thermometer in there and the thermometer temperature went up, that means energy is going from the reaction into the thermometer. So that means energy is being released and lost to the surroundings. The thermometer will be a part of the surroundings. If you put those two liquids together and the thermometer temperature went down, that means the reaction is absorbing energy. It is taking energy away from the surroundings and absorbing it. That's why the thermometer temperature went down. Okay, so that's what they mean by energy gained and energy lost to the surroundings. Okay, so here's our system. Okay. So here they have a gas system, okay? They have oxygen gas and they have hydrogen gas, and that's going to make water, okay? So they're reacting inside of here, okay? This is our container. They're reacting inside of here. Everything else is the surroundings. If they get hotter as they react, then energy is being released. If they get colder, that means energy is being absorbed, okay? The surroundings are everything else. That does not include the hydrogen, the oxygen, and the water, okay? So the piston, the beaker, everything else is considered the surroundings. Okay. Okay. And again, you can have energy absorption or you can have energy release. Okay. This piece. Okay. All right. Let's think about this. When a strong acid is added to a flask containing water, the flask becomes warm to touch. Okay. So we added the acid and then it became warm. So which correctly describes the energy in relation to both the system and the surroundings? So again, I told you the system is the reaction. So the system would be the acid plus the water. That's my system. The acid plus the water. That's my system. Okay. It says the flask became warm to touch. The flask is the container. The container is not a part of the system. Again, the system is just the water and the acid. So if the flask became warmer, that means it gained energy from somewhere. That energy came from the system, and the system is, again, the acid and the water. So in this case, okay, here, that's my system. That's my system. Red is the system. Blue is the surroundings. Okay. The surroundings got hotter. If the surroundings got hotter, that means my change in energy. Again, remember that triangle. Triangle means change. And E is energy. Okay. So my energy went up in the surroundings. So delta E, triangle E, has to be positive. So it's not A and it's not D. Okay. It needs to be positive. The flask temperature went up. Okay. But again, the law of thermodynamics says that energy cannot be created or destroyed, only transformed or transferred. Okay. So the energy that made it go up came from somewhere. Where did it come from? It came from the system. And if the system is giving away energy, that means it has to go down. Okay. So that means that your change in energy in your system is negative. What that means is that it lost energy and that the surroundings positive it absorbed. Okay. And these type of reactions have a specific name. And that's what all this is meant to get to. Okay. Then this is stuff we'll get to eventually. This is nomenclature. Again, I want today to be about the summary. This is what this is all this is leading to. Okay. If a reaction absorbs energy, okay, if it absorbs energy, it is called endothermic. And if it absorbs energy, it is exothermic. Okay. Absorbing is endo, releasing is exo. Okay. So this reaction right here with the acid and the acid in the water released energy and gave it to the flask. It released energy, therefore, this would be a exothermic reaction, okay? This is exothermic, okay? Exothermic, okay? Exothermic is release, endothermic is absorption, okay? And there's a few examples we can look at, okay? The reaction that occurs inside a foot warmer packet is endothermic. What is a foot warmer meant to do? A foot warmer is meant to warm up your feet. Okay, if it's a cold day, put it in your winter boot or whatever. It's meant to warm up your feet. What is the system? What is the surroundings? The packet, okay, the packet itself, anything inside of the packet, that is your system. Okay, the packet is my system. That is where the reaction is taking place. The reaction is taking place inside of the packet. The foot, your foot is the surroundings. Okay. What type of packet is this? This is a foot warmer packet, which means your feet should be getting hotter. Okay. If your feet are getting hotter, that means they're absorbing energy. And if they're absorbing energy, that energy has to be coming from somewhere. And that energy is coming from the packet or the system. Okay. So you have energy going from the system to the surroundings, which means the system is losing energy. And if the system is losing energy, we call that exothermic. Heat is being released. Okay, so this is not true. This is false. How are we on time? This is okay. This is one longer than I wanted it to. Okay. What happens when a hot rock is put into cold water? This one should be intuitive. Okay, you put something hot and something cold. What's going to happen to the hot rock? The hot rock is going to get colder and the water is going to get warmer. Okay, so the water and rock will both gain energy? Not true. They cannot both be gaining energy. The water and rock will both lose energy. That is not true. Okay, you're combining them together. There needs to be a total amount. The rock will gain and the water will lose. Which one is warmer? I told you energy goes from hot to cold. The rock is the hot, the water is cold. So the rock will not be gaining energy. The rock will be the one giving up the energy. So the rock will lose the energy and the water will gain it. Okay. If you put a hot rock in cold water and your system is the rock, okay, this is the important part. Okay, they're saying the system is the rock. If the system is the rock, then the process is going to be exothermic. And it is exothermic because the rock is, again, the rock is losing energy. Okay, it's releasing it, giving it away. If the system is water, it's the exact same question. But if the system is the water, then the process is endothermic. Okay? It's endo because then the rock is, or the water is gaining energy. Okay? So that will be endo. Remember, absorption is endo, release is exo. And then I'll do one more because again I don't want to make these videos too long. And you can look at the other examples from our practice. If you put an ice cube in water and your system is the ice, the process is considered to be what? Okay. The system is the ice. If you're putting ice in water, it's because usually you want to cool down the water. So let's make the assumption the water is the warmer thing in this case. If the water is the hot thing and the ice is the cold thing, that means the energy is going to go from the water to the ice cube. So if the system is the ice, then this is going to be endothermic, okay? The energy is going to go from the water to the ice. That's what's going to make the water colder, okay? So that would be an endothermic if the system is the ice, okay? So that's it for today, guys. We will continue with thermochemistry on Monday. I didn't want to make today too extravagant. Okay, I just wanted to focus on the introduction. Just endothermic and exothermic. Energy release, energy absorption. That's all that you get in a chemical reaction. Of course, we can talk about it a lot more in depth, but that's all you need to know for now. Okay, release and absorption. Those are your only two options. Okay. Happy Friday. Hope you're all doing well. There is a worksheet for you to do. The worksheet is intuitive. It's just 5 multiple choice questions. Okay, it's not heavy. I don't even think that has any math related to it. It's just if you understand this concept, you're good to go. You're golden. Okay, but it's just 5 multiple choice questions. That's all you got to do for today. Okay. Happy Friday. Wish you all the best. Take care. Enjoy.